All right, the mean value theorem. Now, unfortunately, there's several theorems in calculus that have practically the same name. They got mean in them or theorem in them, for example. So it's going to get a little bit annoying for you to try and keep track of which is which. Usually, though, you'll get a hint from the problem. So in this chapter, we're going to look at two of them, the mean value theorem, and then the next video, Rawls theorem, which is really just a special case, the mean value theorem. But because these two involve derivatives and average values and stuff, hopefully you'll see from the context that since all the problems they can ask about these two are exactly the same, or they're all very similar, you'll be able to, you don't have to necessarily know what it's called in order to do the problems. So we'll take a look. All right, so what is the mean value theorem? Well, mean you'll probably recognize from algebra and everywhere else. Mean just means average. So when we're talking about derivatives, the mean value in this case is just the average rate of change of the function. So rate of change of the derivative is just slope, right? So basically, if you're going from point A to point B, and they'll probably label this little a being the x-coordinate, and this being little b is just the x-coordinate of point B. So when you're going from A to B, what's your sort of average slope as you move from A to B? So you're going downhill, right? But you start out, like in this first drawing right here, you start out going pretty level, then the hill takes a big dive, then it levels out a little bit. So we kind of have this non-constant slope, right? We start more level, then we get steeper, then we get leveler again. So what they're saying with the mean value, and the way we're going to treat the mean value in this type of problem, is just what's the average slope between point A and point B. And you'll notice that even though I drew 4 different scenarios here, they all have the same average value, because the way you find average value of slope would just be rise over run between point A and point B. So it'd be y, y of the second point minus y of the first point divided by x of the second point minus x of the first point. If we replace these 1s and 2s with a's and b's, you can see there's just a totally standard rise over run formula between point A and point B. And since all 4 drawings I made here have the exact same point A and B, then you can see that, they're all going to have the exact same, this thing's going to be the same for all of them. The average slope between points A and B is constant, even though this one goes crazy steep, dives way down, but then swoops up and ends up at B. Or this one, is just the same one we saw before, just swoopy, but we could do, whoa. We could go scribble like crazy on our way to B. Or we could do this one where we, it's like, even though these all have different shapes, they've got the same average slope, and that's the really weird thing about this situation. But with the mean value theorem, what we're going to do is we're going to say, hey, you know what? There's probably a point between A and B where no matter how many swoops and dives it takes, there's probably at least one point where the slope of the curve is the same as the slope between A and B, as that average slope. So if you draw sort of a dashed line, if you draw a dashed line between A and B, you can see the slope of this line is kind of like that. There should be a point somewhere on the actual curve, the swoopy-doo one, that sort of matches that same thing. So if you sort of take that angled line and move it down a little bit, you'll see that there's sort of a parallel line right here where the tangent line to the curve is parallel to that average slope between A and B. And that's the point we're looking for. We're looking for the point where the slope of the tangent line of the curve is equal to the slope between A and B. And the mean value theorem says that there must be a point like that. So as long as this curve is continuous, no matter how it swoops and dives, there's got to be a point somewhere. And all these drawings we've got here, we can find a point that's kind of like that. Like in this one, we got, somewhere right in here is actually a tangent. So that's what we're working with. Let's do some examples. So the way it's going to work is they first might ask you, hey, does the mean value theorem even apply to this situation? And the key there is it's got to be differentiable. So if we had, in all the previous drawings I drew, we had stuff like going from here to here. And yeah, as long as you can draw the line, draw the curve without leaving the paper, then that's fine, that's differentiable. But what if we had something like this, where point A and point B are like this, but then this shoots up, and then it shoots down from infinity on either side of an asymptote or something. Now we got a different situation. This is not a continuous function, it's not differentiable, so this doesn't apply. The way you spot differentiable stuff is just it looks like a smooth curve, like how a polynomial would look. Just kind of a smooth, gentle, curving deal, no missing points, no sharp corners. That's when the mean value theorem applies. But once it does, it's pretty simple. You just find the slope of that average line. Just connect, find the slope of between A and B. I wrote it before as y minus y over x minus x, but if you look at one of these graphs, that's really just the y-coordinate of point B. So the y-coordinate of point B is going to be f of B. The y-coordinate of point A is going to be f of A. So we just take the difference of those as the rise, and then the run is just the difference between the x-coordinate of B and the x-coordinate of A, which is B minus A. So that's where this formula comes from. It's just the average value formula is just rise over run, but like in function notation form. So you just need the y-coordinate of B. This is just the y-coordinate of B minus the y-coordinate of A divided by the x-coordinate of B minus x-coordinate of A. Once we find this average value, and I know there's a lot to take in a second we're going to do a bunch of practice problems, but once you find that average value, it's really simple. You just take the derivative of the function, set it equal to that number you just got, and solve for x. Because usually what they're asking for is the point, they're asking for that x value, like where in between A and B, at what x value would that slope equal that? All right, so let's take a look at a graph we know really well. I always use f of x equals x squared, which is a basic parabola. I always use that one because everyone knows what it looks like. So so you won't have to sit there getting confused just by the graph. And we've got an interval to work with, and on these mean value problems, there's always an interval. They'll always give you a 0 to 4 or whatever, because if it went from negative infinity to infinity, who knows what the average value is? You got to have a point A and a point B to work with to begin with. So we're always going to have a point A and a point B, and their x value is always called A, and the other value is always called B. So let's plug and chug. First, we need step 1 from the previous page was find the average value. And that's just going to be f of B minus f of A over B minus A. So basically, we just want to find our 2 points. So because it's on the interval 0, 4, I've got this point and I got this point. But since we know what this graph looks like, hey, let's just draw the actual parabola. So an actual parabola goes like, and so the point A is at 0, and that is going to be 0, 0. And then at the other end of our interval, point B is going to be at 4. X equals 4, and then what is the y value? Well, it's just 4 squared, because we plug in 4, f of B, f of 4 is just going to be 4 squared, which is 16. All right, so we got our 2 points. That means our average sort of slope is kind of like this dotted line, and its slope is just going to be 16 minus 0 over 4 minus 0, which is 4. All right, so step 1 accomplished. We found the slope of the line connecting our 2 endpoints. This is really just plug and chug at this point. So now the slope is 4, so what we're going to do is take the derivative of the original function and set it equal to that number we just got in step 1. The original function is x squared, so the derivative is just 2x, and we just want to set that equal to 4. Right, this is obviously a pretty easy one. Just divide both sides by 2 and you get x equals 2. Alright, so x equals 2 is that magical point where the slope of the tangent line, so that's 2 is halfway between 0 and 4, so that's like right here. And obviously, this is not an amazingly to scale drawing, but you can kind of see how the tangent line at x equals 2 is pretty parallel to that average line. So we're all set. And then the other question they might ask you is, what is the value of that point? Like, what is the point at which this whole average value equals the instantaneous slope? And that is going to happen at x equals 2. And then to get that y value, we just plug back into the original formula. So we just plug in back in x squared. 2 squared is 4. All right, so this point right here where the slope of the curve is parallel to that average slope happens at the point 2, 4, which is halfway between the two. And that makes a lot of sense, right? All right, let's take a look at another one. So this time I said find C. What C means in the mean value theorem, what they're saying is on the interval A to B, find a point C. So that point C is just, if the interval is from A to B, B is just that number between A and B that solves the problem. All right, so we got f of x equals this, and the interval is -2 to 2. So step number 1, average value is just going to be, this time I'll just plug in numbers, so it's going to be f of B, the second point, so that's f of 2, minus f of A, which is -2, all over B minus A, so 2 minus negative 2, which gives us 2 plus 2. All right, so f of 2 is just 2 cubed is 8. And then negative 2 cubed is negative 8, so plus 8, because the negatives cancel. And then we got 2 plus 2 is 4. All right, so the average value is 16 over 4, which is, once again, 4. That's kind of silly. All right, let's check it out. So now step 2 was just set 4 equal to the derivative, because I want to know the value of x where the derivative is equal to 4. So I'm going to just take the derivative, which in this case would be 3x squared, because the derivative of x cubed is just 3x squared with the power rule. And I want that to equal this number I just got, which is 4. Oh man, there's going to be some roots. All right, so we got to divide both sides by 3 first. So we get x squared equals 4 thirds, and then square root both sides, and you get x equals, now this is a tricky one, this is a plus or minus situation. We got to put the plus or minus out front. When you solve an equation that has x squared in it, and then the way you're solving it is by taking the square root of both sides, that's when you need the plus or minus. You don't want to forget that. In a second we'll take a look at what this graph looks like and see why it makes sense that we have two answers. So plus or minus square root of 4 is just 2, and the denominator is root 3. And if you really wanted to, you can rationalize this by multiplying top and bottom by root 3. So we get plus or minus 2 root 3 over 3. All right, so let's take a look at why this graph would have two answers. Apologize for my lack of straight lines today. All right, so what does the x cubed parent graph look like? Anyone? It looks like kind of disco. Goes up like that, but then negative numbers give you negative cubes, so it goes like that. All right, so this is the graph, and we're taking an interval from negative 2 to 2, so maybe negative 2 right there. There's our point A, and then our point B. It's like up here at positive 2. All right, so what does our average slope look like? Well, it's a pretty steep, it's a fairly steep line. And this point is actually 2 comma 8. And this point down here, A, is negative 2 comma negative 8. So this is actually a very steep line, slope of 4. But you can see how because of this thing's shape, there's actually two spots. I'm going to zoom in on this little area to show it a little bit bigger. We're looking for the 2 points on this section of curve. If there's B and there's A, we're looking for the two spots on this section of curve where the slope equals 4. So we're looking for kind of a steep up to the right. You can kind of see though, there's one right here where the tangent function looks like that, but there's also one over here where the slope is also parallel to that sort of average line between A and B. So if you take the dotted line, is what I found in step A, that has a slope of 4, just with rise over run between A and B. And then the other two answers are going to be the x value. The x coordinate of this point is going to be 2 root 3 over 3, and then some crazy stuff for the y value. And then the one right here, the x value is going to be negative 2 root 3 over 3, comma, whatever crazy stuff you get when you cube that. So that's why there's 2 points, is because just the nature of this curve is it hits a couple of different spots that are actually parallel to the mean, the average slope. And by the way, I'm not going to do it just because it would be such a mess for x cubed, but the way you would get, I mean, it's not that bad. The way you get the y coordinate of either of these points is just take f of the x value, right? So if the original function is just x cubed, if you want to find any point along it, all you do is plug in an x, get out a y. So if you want to plug in, like point B here would be, we said the x coordinate is 2 root 3 over 3, but what's that y coordinate? Well, it's just f of 2 root 3 over 3. So if we plug and chug this through the cubing process, it's going to be 2 root 3 over 3. And then what happens if you cube 2 root 3 over 3? Let's see, 2 cubed is 8. Square root of 3 cubed is 3 root 3. And 3 cubed is 27. So now you could probably simplify all that, but the point is, to get the y value of any point, you just plug in the x value into the original function to get out y values. All right, that was crazy. Let's see what happens on this next one. So once again, find C, whatever, find the point at which satisfies the mean value theorem. for square root of x on negative 3 comma 3. All right, so let's take a look. Now, the first thing to do, well, first you want to figure out the average slope, but that's pretty easy. So step 1, the average slope is just you plug in negative 3 and you get 3. Plug in positive 3, you get 3. So this is actually, these 2 points are right next to each other. And if you recall, what the absolute value of x looks like is just a V shape. So what we're looking at here is an average slope of 0, because we're just looking at 2 points that are sort of on either side of the vertex of this V. And of course, since it's just absolute value of x, that is right at the origin. Just sort of irrelevant to Evans's problem. So negative 3 and 3. All right, my 3's are terrible. So that's what the graph looks like. It makes sense we got an average value of 0. So step 2, now we need to set the derivative equal to the number we got in the first step, right? But what is the derivative of x, absolute value of x? That's a tricky one. It turns out there's not actually a formula. To figure that out, you sort of have to break up the absolute value of x into an x for positive numbers and a negative x for whatever. Point is, what we really want to do is be looking at it graphically. Because if you ever see a problem with an absolute value of x in it, what you probably should be doing, like 99 times out of 99, is just think of it graphically, think of that V shape, and then start working from there. So if you look at what's going on here, what is the mean value theorem says that there's a spot between point A and point B where the derivative is equal to that horizontal line, right? So since these are sideways to each other, they're horizontal to each other, that means we're looking for a spot where the slope is 0. We're looking for a horizontal tangent line. But does that ever happen? It doesn't, because this section is all slope a negative 1. This section is all slope a positive 1. But what's going on at that corner? The only chance we'd have to have a derivative of 0 is right at that corner, because the slope is always a different constant everywhere else. But what happens at the point of an elbow? That is an undifferentiable point. And I just put this, so this is a trick question, and I only threw it in there because this is the kind of trick question they always ask on tests about this chapter, is that the function has to be smooth and differentiable all along the interval. So the problem we've got on this one is that it's not differentiable because that sharp corner, this just has an undefined slope. You know, if you approach it from the left, it kind of looks like it's got a negative 1 slope, but going to the right, it's got a positive 1 slope, and it's sort of infinitely sharp. So this single point, you know, there's just no slope possible here because either it's 1 or it's negative 1, but it can't decide, and neither do you, right? You can't decide either, so that's just an undefined slope. So it turns out sharp corners totally screw up both the mean value theorem and Rawls' theorem. All right, turns out we have another funky trick question that's not defined everywhere. What's wrong with this one? Once again, we have, you know, matching endpoints. But the real problem here is we have a couple of asymptotes. Because this thing is undefined at x equals 2, so x cannot equal negative 2 or positive 2. And the way you would figure that out is just by factoring the denominator. So you get x over x minus 2. And at that point, if you remember from pre-calculus, it's pretty obvious that if you plugged in 2, you'd be dividing by 0. And if you plugged in negative 2, you'd also be dividing by 0. So that's why it's undefined. But because it's undefined, there are a couple of spots on our interval, because our interval includes both negative 2 and 2. So since it includes those, can't do the problem. It's not differentiable. And if you graph this thing in your calculator, you'll see that's pretty funky, and there might not be a spot where the slope is actually equal to those things. All right, so step by step. Hopefully these steps, even though they looked like a lot of Greek at the beginning of this video, hopefully you kind of see what we did. All we do is we find the average slope between point A and point B, and that's just difference of y values over difference of x values. Then we take the derivative of the function and set it equal to the number we got in step 1 and solve it for x. And that x is going to give us our c value. So anytime they're asking for c or talking about c, what they're really talking about is this middle value. All right, so stick around for Rawls' theorem, which is just sort of a special case of the mean value theorem.